All right, guys, so I was looking for another cone problem. So this is a continuation of the cones. I had an interruption and then I made a mistake during my interruption. So here's another cone problem. We have a conical paper cup that is 10 centimeters tall with a base radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. So at what rate is water being poured into the cup when the water level is 8 centimeters? So again, I have this liquid surface with some radius r, and I have some depth, which I'm going to call h. Now, they're telling me that the water level rises at a rate of 2 centimeters per second. So dH dt is equal to 2. Okay, so I'm just making my little picture and writing down what I know. And what are we trying to find? We're trying to find the rate at which water is being poured into the cup. So we're trying to find the rate at which the volume is changing when H is 8. That's an H. So let me move this over to a clean piece of paper, and we'll get started here. So again, this is 10, this is R, this is H, this is 10. All right, I know that dH dt is equal to 2. And I also know that dV dt is what I'm looking for when the depth is 8 centimeters. All right, and I've got a cone. So the volume of a cone is 1/3 pi r square high. All right, and now what I need to do is I've got my picture. I've got a geometric formula. Oh gosh, this thing. Sorry. So annoying. I've got a geometric formula. I know what I'm looking for, and I know that the depth is increasing at a rate of 2 centimeters per second. All right. So at this point here, what I can do is I'm going to do similar triangles. R is to 10 as H is to 10, right? Radius is to radius as depth is to depth, or height is to height. So R is equal to H. Well, that's nice because when I plug that in, remember we're trying to get rid of R here because remember I've got DH and DV, so I don't need a DR. Okay, that's going to hurt me, not help me. So we have V is equal to pi over 3. We're going to replace R with H. We're going to square it. We're going to multiply by H. So V is equal to pi H cubed over 3 is my compacted little formula. So now I can take the derivative. dV dt is equal to. So again, if you want to pull this number out to the side and focus on the derivative of this part, then do that. So we've got pi over 3 times 3h squared h prime, or dH dt. So now I'm mixing my notations, and I really shouldn't do that. I should call this dH dt. But, you can use whatever you want. Just make sure it's consistent. Do as I say, not as I do. And in fact, it's bothering me so much because you are taking the exam that I'm going to change that to dH dt. So if I would have written V prime, then I could put H prime. But I did dV dt, so I should have dH dt. So these 3's here are going to cancel. So I have the rate of change of the volume is equal to pi h squared dH dt. And now I can plug in what I know. Well, what I know is that I'm looking for dV dt, and I know that dH dt is 2, and we want to find the rate at which the volume is changing when the depth is 8. So I have pi times 8 squared times 2. So dV dt is equal to, so this is 64, and 64 times 2 is 128 pi. All right, so, and we're looking for volume, so that's going to be in units cubed divided by time. All right, so what can I say? I can say, so the question was, at what rate is the water being poured into the cup when the water level is 8 centimeters? I can say the water is being poured into the cup at a rate of 128 pi cubic centimeters at the moment that the water level is 8 centimeters. All right, so there's your cone problems. So I'm kind of doing 2 of every problem here. Let's do a winch. Winches. All right. This is problem number 12 from your book. And again, it's on page 235. So we have a winch at the end of a dock. So remember, a winch is just a little, like a pulley. Like, so here's a dock, right? This is the water. This is the top of the dock. And there's some little winch, little circle with a string on it, or a rope on it, I should say. If it's pulling a boat, it's not going to be a string. A winch at the end of a dock is 10 feet above the level of the dock. A winch at the end of a dock is 10 feet above the level of the deck of a boat. So here's your boat. This is the deck of the boat, sailboat. All right, and you've got some rope. All right, so you can think of it like this. All right, so a winch at the end of a dock is 10 feet above the level of a deck of a boat. So this is 10. A rope is attached to the deck. So here's my rope. And it's being pulled in. So this is a terrible picture. Let's make the winch look like that. And maybe there's somebody here, you know, pulling the rope in or something like that. But the rope attached to the deck is being hauled in by the winch at a rate of 5 feet per second. All right, so this is 5 feet per second. And I'm going to call this dz dt. And I'll show you why in a second. It's actually a terrible picture. Oh, it's a really bad picture. All right. Anyway, how fast is the boat approaching? So as this thing's being wound up like a fishing line, right? We're winding this thing up and the rope's pulling this thing in. The boat's headed this way toward the dock. So we'll call this the dock here, I guess. Again, really bad picture. But the boat's headed in this way. So we want to know how fast is the boat approaching. We can call that dx dt when there are 26 feet of rope out. So what happens is, and again, you know, I cannot draw, but this is a right triangle. I know, it's really, really bad. Let me see if I can find a picture somewhere of something a little nicer. Any picture in here anywhere of a winch? There isn't. Okay. Let me see if I can look one up. Okay, good. Here's a picture. It's actually a YouTube video, but let me just make a copy of this real quick so you can get a better idea. Copy, paste of what I'm trying to portray, because I'm just really terrible at drawing these things. So, okay, file, print. So again, sorry about the little delay, but I'm trying to get all of this done tonight. And like I said, today was kind of a busy day because I had testing going on, but this is ideally a picture. Let me go back to my YouTube video so I can make sure we're in focus. Here we go. Live stream. Okay. All right, so this is not the scenario that we have. Okay, so this is the boat here. And I don't know, that's the deck of the boat. And I'm going to change this because the height of the dock in our case is 10 feet. Okay, so this is 10 feet. And they're calling this x of t. Now look, the height of the dock is not going to change, right? It's a constant. This rate at which the rope is being pulled in, that's going to change, and the rate at which the boat's headed toward the dock is going to change. This thing is going to remain constant, and what we have is a right triangle. So although I cannot draw those things very good, that's how it ends up, okay? And what I do know is that, so x of t, or I can say dx dt, we're looking for the rate at which the boat's approaching the dock. How fast is the boat approaching the dock when there are 26 feet of rope out? So again, we'll call this z is 26. So I don't know what dz dt is either. Oh, I do. It's so the rope is being hauled in at 5 feet per second. Now look, I have to attach a minus. Why? Because the rope is getting, as the boat's approaching, the length of this rope is getting smaller and smaller and smaller. So I need to multiply that by a negative, or include that negative there. All right. So again, I'm going to use x squared plus y squared is equal to z squared. Now this is constant. All right. So x squared plus 10 squared is equal to z squared. This I can plug in right away because the derivative of that's going to be 0 because there's no change. So let's take the derivative. We have, and I'm going to multiply through by 2. So we have xx prime equals to zz prime. All right, and what we're looking for is x prime, or dx dt. Well, I have to find a couple of things. Well, I have to find one thing. I know what z is, and I know what y is. I didn't find what x is, right? So I just do 26 squared minus 10 squared is 576, and so x is 24. So by Pythagorean theorem, I found my value of x. Now I can just plug in. So I've got 24 x prime is equal to 26 times negative 5. So x prime is equal to 26 times negative 5 over 24, right? And, 2 goes into here 13, 2 goes in here 12. And so what I end up with is 13 times 5 negative divided by 12. So, I could write this as negative 65 over 12 and leave it like that, or I could write it as negative 5.417. Remember with AP, you round to 3 places past the decimal. And so anyway, how could I answer the question? Well, the question was, how fast is the boat approaching the dock when there are 26 feet of rope out? And I can say, and again, this negative, I'm not going to say the boat approaches the dock at a rate of negative 5.417 feet per second, because, again, this boat's getting closer and closer to the dock. So this just means it's approaching the dock, all right? So I can say the boat is approaching the dock at a rate of 5.417 feet per second when there are 26 feet of rope. Okay, so that's a little winch problem. And I don't think there's going to be another winch problem in this book. There isn't. So, again, I don't know if I put one in WebAssign or not. They have a new feature now called a randomization, and I just ordered that, or I chose that, and it randomized, however many questions I tell it to on that topic. So I don't even know what the questions are. So I don't know if there's a winch problem there or not, but I'm suspecting there is. And in the meantime, just in case there isn't, I will try to find some more winch problems. You can look them up online and you'll see them there. All right. So I covered the classical problems where we're using, spheres, circles, right triangles, right? So this was right triangle, this was right triangle, that's right triangle, and cones, similar triangles, right? And now we need to talk about the more difficult problems. So like moving particles and things of that nature. So let's see here. Woo! Let's see. So in your book, number 11. So new problem. And in number 11, make sure this is straight. You're being told the following. A particle is moving along the graph of y equals to root x. So a particle is moving along this graph. And you know this graph looks like this, right? So a particle is moving along that graph. At what point on the curve are the x and y coordinates of the particle changing at the same rate? So what I'm interested in is the x and y coordinate changing at the same rate. So what I'm looking for is when is dy dt equal to dx dt, right? Does that make sense? It's not hard, but it's something you've got to think about. All right. And so what I know is that, I've got this simple little function y equals to root x here. And if I take the derivative, because there's nothing else to do with that, I get y prime is equal to 1/2 x to the negative 1/2, which is 1 over 2 root x. Okay, so what I know is dy dt is equal to 1 over 2 root x. So what I'm looking for really is, when is dx dt equal to this thing, right? So when is dx dt equal to 1 over 2 root x? So if this is the case, now look, the particle is in motion, all right? So what I can do here is, let me think, hang on a second. We definitely want them equal. Yeah, I'm an idiot. I forgot my dx dt. Okay, so look, this is implicit differentiation. Scratch this for a second. It's right, but I forgot something here, right? So if I take the derivative on the left, I get dy dt. If I take the derivative on the right, I get 1/2 x to the negative 1/2 dx dt. So I forgot my dx dt. So dy dt is equal to 1 over 2 root x dx dt. All right? Does that make sense? However, dy dt is equal to that same thing. So what I can say is, I can say dx dt is equal to 1 over 2 root x dx dt, because I want dy dt to equal to dx dt. So all I'm doing is I'm replacing this with this. Does that make, I hope that makes sense. I know it's a little confusing. Okay, so what this means then is that, dx dt is going to either equal 0, okay, and that cannot happen because the particle is moving. Okay, so the rate of change in the x direction cannot equal to 0 because the particle is in motion. Or 1 over 2 root x is equal to 1. So in other words, if I divide both sides by dx dt, I get 1 is equal to 1 over 2 root x. This has got to be the case. All right, well, when does this happen? Well, if I multiply both sides by 2 root x, I get 2 root x is equal to 1, right? So root x is equal to 1/2. Sorry. And if I square both sides, I get when x is equal to 1/4. Now, I'm not going to use plus or minus. I'm only going to use the positive because I can't have a negative value there. I can't have a negative under a radical. So when x is equal to 1/4, so the desired point that you're looking for in the curve when this happens, when their rates are exactly the same, is going to be at the point when x is equal to 1/4. Well, if x is equal to 1/4, what's y? Well, y is equal to the square root of 1/4, which is 1/2. So the interval would be 1/4, 1/2. See if I can find another one. I think I saw one. These papers, no. See if I can find another little moving particle. No. So I'm looking at the best book right now, and there's not another example. Let me just see if there's an example. No. So there's not another example in the book. Oh, yes, there is. Yes, there is. Yes, there is. My bad. So in problem number 8, so let me get rid of this. This here. So in problem number 8 of the book, it says a particle is moving along the curve y equals x squared in such a way that when x is equal to 1/2, then dx dt is equal to 2 feet per second. They want you to find dy dt at that moment, or when x is equal to 1/2. All right, so let's differentiate our function. So the nice thing is about the little particle motion functions, you just differentiate. So let's not forget my dx dt. So we've got dy dt on the left is equal to 2x dx dt on the right, right? And so we know that dx dt is 2. So at this point here, I've taken the derivative, and so I can plug things in, and I'm looking for dy dt. So dy dt is equal to 2. Now we want it when x is 1/2 times dx dt. Okay, and I can get rid of a couple of 2's there. So I can say dy dt is equal to 2 feet per second. How would I interpret that, or how would I write the interpretation? I could say something along the line that the change in y at the moment when x is equal to 1/2 is 2 feet per second. Okay, so it is a coincidence that dx dt was 2 and dy dt is also 2. Anyway, that's how you would solve a particle in motion type problem. Okay, now we're going to do shadows. And I know that we covered some in class. Most of you don't like them, but you could definitely get a shadow problem. So nothing's off the table, especially now. And let me tell you, they assured us that they are not going easy on you guys on this exam. So I don't want to leave any stone unturned. So we did this. Well, let's look at shadows. All right. So, all right, number 15. Now, shadows are not bad. Shadows are right triangles, just like other things are right triangles. So let's look at number 15 from your textbook. And that's a shadow problem. And there are lots of shadow problems on the net, and I think there's definitely one in those papers. So let's have a look at this one and see. So this is what it says. It says a street light is 15 feet above a sidewalk. So here's the light, and it's 15 feet, and this is the sidewalk. Okay? And it says a man 6 feet tall walks away from the light. So here's a man, and he's 6 feet tall. This is 15 feet. And he's walking away from the light. Carol Ann, go to the light. Anyway, freaky. And he's walking away at a rate of 5 feet per second. Right, so since he's walking away, it's a positive 5. If he was walking toward the light, it would be -5, right? And so this is what you do. You do this. Okay, so you see I've got a big right triangle and I've got a little right triangle, right? So the guy himself forms this little right triangle here. And then the street light and the ground and its hypotenuse forms the big triangle. Okay, so by the way, the top of his head to here, you can use this triangle too if you want to. So for instance, if he's 6 feet tall and the pole or the lamp is 15 feet above the ground, that makes this little piece 9, right? And the distance between this person, this guy, and this lamppost is some x. I don't know what it is. And his shadow, if he's walking away, the shadow is going to be in front of him. So I'll call it, I hate calling it S because my S look like 5s. So I'll just call it S. Shadow. It's an S. Okay, so the shadow is going to be in front of him. All right, so it says A, determine a function relating the length of the man's shadow to his distance from the base of the street light. Okay, so the length of the shadow is S, and the distance, so we know that, we established that, and the distance between the guy and the light is some X, right? So this is what I can do. I'm going to use similar triangles. Okay, so again, with shadows, we're going to use similar triangles. So what I can say is, I can say this shadow length is to the height of the man, as the length between the man and the pole is to this distance here, 9. And that tells me that S is equal to 6x over 9, or a little nicer, we can divide by 3, so we have 2x over 3, or 2/3 x. In part B, it says, determine the rate at which the man's shadow is lengthening. So what we want to find is we want to find ds dt. What is the rate that it's lengthening at the moment he's 20 feet from the pole? All right. Are you seeing all that? There we go. Okay, well, I need to take a derivative. So I'm going to use S is equal to 2/3 x. So ds dt is equal to 2/3 dx dt. This is what I'm looking for. I know what dx dt is. He's walking at a rate of 5 feet per second away from the light. So I can say ds dt is equal to 2/3 times 5, which is 10/3 feet per second. Voila. Fini. I'm done. That wasn't so bad now, was it? Now, granted, you need to make that picture. And remember that when you're walking away from a light, your shadow's in front of you. If you're walking toward the light, the shadow's behind you. Those two things you need to remember. But just remember that the height of the person is to the length of the shadow, as is, the distance from the light to the person is to this height or length here. Let's see if there's another one in here. Shadows. Oh, there is. Look at this in this papers here. Let me put this right here. Oops, this one. Okay, so a 7-foot tall person is walking away from a 20-foot lamppost. So right away, here's my light, here's the ground, here's the guy, and he's 7 feet. This is 20 feet. And I know I'm going like this because I'm on a right triangle. He's walking away at a rate of 5 feet per second. Assume the scenario can be modeled with right triangles. All right. At what rate is the length of his shadow changing when he's 16 feet from the lamppost? Now, this is a little bit different. All right. So we're going to call this X again, the distance between the person. So this is the guy, right? The distance between the lamppost and the guy we're going to call it x, okay? And again, we're going to call this S for shadow. So what I'm going to have is x plus s. So this whole distance here to the tip of the shadow is x plus x, right? X plus s. So I'm going to say that this is to 20 as, now look, y is to 7. How would I do that? Well, this is so I'm doing this is to this as s is to 7. So that's an s, not a 5. And now I can just cross multiply this thing if I want to. And take the derivative. What am I looking for? I'm looking for the rate of change of his shadow when he is 16 feet from the lamppost. Is that okay? So what I'm going to have is 7 times x plus, again, this is an s, equals to 20s. And let's see, that's going to be 7x plus 7s is 20s. If I subtract 20s from both sides, I have 7x is equal to 13s. So let's solve this thing for s. So s is equal to 7 over 13x, right? So if I take the derivative of both sides, I get ds dt is equal to 7 over 13 dx dt. I know what dx dt is, it's 5. So if I plug the 5 in for dx dt, I'm going to have 35 over 13 feet per second. So what I can say is the length of the person's shadow is changing at a rate, and in fact, I'd probably say increasing at a rate of 35/13 feet per second at the instant or at the moment when he is 16 feet from the lamppost. Is that okay? And again, you could have done this too. You could call this x, right? These two distances are the same. And this would be, this piece here would be 20 minus 7 or 13. And you could do this is to this, is that, is to that if you want to. All right. So I just wanted to show you 2 ways. And you will have a shadow problem on WebAssign. So you can fight with that a little bit. All right. One last thing, and these are my favorites, are the theta, we call them the theta problems, but they're changes in angles, right? And they're really, really not that hard. So let's look at this problem right below the one we just did. We have an observer who stands 700 feet away from a launch pad to watch a rocket launch. The rocket blasts off and maintains velocity 900 feet per second. Assume the scenario can be modeled as a right triangle. They usually always are. How fast is the observer to rocket distance changing when the rocket is 2,400 feet from the ground? Okay, so let's make a picture. Here's the observer. Here's the rocket. Here's the launch pad here. So this is the observer. He's 700 feet away from the launch pad. The rocket blasts off. This is the rate at which the rocket maintains a velocity. Okay, it's going to be dy dt is equal to 900. Now, the other thing I wanted to say is that this distance will not change, right? This rocket's going to go up and up, and as the rocket goes up and up, the guy's looking up at the rocket, right? So there's this angle theta in between the ground and this guy's eyes and, or his head. And as the rocket goes up, his head's moving back and he's looking up and up and up and up. And this distance, as the rocket, goes higher and higher, is going to get bigger and bigger and bigger. All right, so we want to know how fast is the observer to rocket distance changing. And in fact, this isn't even a theta problem. My bad. We could turn it into one. This is just a right triangle. When the rocket is 2,400 feet from the ground. So what I know is that y is 2,400. Okay, I'm going to call this z. And what we're trying to find is dz dt, okay, when y is 2,400 feet. So yeah, unfortunately, this did not turn out to be a theta problem. I didn't read it well enough. So Pythagorean theorem, right? So this here can be our x. So we have 700 squared. That's not going to change. Plus y squared is equal to z squared. This is going to change as the rocket goes higher and higher into the sky, and this distance is going to change, right? So the derivative now is going to be 0 plus y prime equals zz prime. And y is 2,400, and y prime is 900, and that equals to z. Well, I didn't find z. Z is 2,400 squared plus 700 squared. So 700 squared plus 2,400 squared is equal to a horrific number. But when squared, we get 2,500. Okay, so this is 2,500 z prime. So z prime is equal to 2,400 times 900 is, again, another horrific number. It's 216,0000 over 2,500. If I divide that by 2,500, 2 zeros cancel, and we get 864. That would be feet per second because this is linear. So anyway, I could say that the observer to rocket distance is changing or increasing at a rate of 864 feet per second when the rocket is 2,400 feet from the ground. Not a theta problem. And I could change this into a theta problem if I wanted to, but I kind of don't want to because depending on some things that I choose, I could make it kind of difficult. So I want one that works. So let me see if I can find a theta problem real quick. So let me go on to the internet very quickly. Bear with me. I'm sorry. Here's some. Yeah, the ladder provides a nice one too. Okay, well, let's do a simple ladder problem because you're familiar with those. Let me get rid of all the papers here. And so I just found one online. And actually, let me just print this. I just can't print. Print. Okay, so I'm going to slide this under the camera in just a second. There it goes. Okay. Yeah, here we go. Oh, goodness, it's printing everything. Okay, so here's the scenario. Oops. A 10-foot ladder leans against a house on a flat ground, right? So I'm going to move this up. Here's my ladder. It's 10 feet. This is the house. This is the ground, obviously. The house is to the left of the ladder. Okay, like I don't think it would matter. But anyway, the base of the ladder starts to slide away from the house at 2 feet per second. So we know that dx dt is equal to 2, right? At what rate is the angle between the ladder and the ground changing? So this is my theta, right? As this ladder is sliding, as the top's falling down, this angle is getting smaller and smaller. So at what rate is the angle between the ladder and the ground changing? So we want d theta dt when the base, this is the bottom of the ladder, is 8 feet from the house, when x is equal to 8. So this is 8. Now again, the length of the ladder is not going to change, so that's really nice. We don't have to worry about that. So again, we have this triangle, right? And I want to say, you know, x squared plus y squared is equal to 10 squared, right? I need to move this up a little bit, so bear with me here. All right, so we have x squared plus y squared is equal to 10 squared. And everything here is labeled. This is, so I can find my y, right? So this is 100 minus 64 is 36, so I guess y is 6. So in things like this, what I know is that I have this little triangle with some theta here. This is 6, this is 10, and this is 8, right? And so generally speaking, a lot of times we're going to use the tangent, but you can use whatever works for you, all right? So we have to use trig functions here, and that doesn't really make it difficult. But if you're looking for an angle changing, then you have to use a trig function. So what I'm going to say is the following, right? I'm going to say that the cosine of this angle theta is equal to x over 10. Now, why didn't I plug an 8 in there? Because I need a function that I can take the derivative of. All right, I know that x is 8, but this is changing, right? The ladder's sliding. So the top of the ladder sliding, the bottom of the ladder sliding, this angle sliding, but the length of the ladder is constant. So I want to include that constant in there, but I still need a variable in terms of x and theta, which is why I chose the cosine. Now I could have used the sine or whatever, but cosine and tangent are generally the two that we use the most. Just saying. You can use any trig function you want to, but the easiest ones are the tangent because the derivative is the secant squared, which is 1 over the cosine squared, or the cosine. So anyway, we're looking for d theta dt. So I have a theta, and in relation to x. So I have a theta and an x. So that's what I'm looking for. And again, I could have used the sine of theta is equal to y over 10 if I wanted to, right? Opposite over hypotenuse. But this is the formula that I need so I can take a derivative. So let's take the derivative. If I take the derivative of the left, the derivative of the cosine is the negative sine of theta, d theta dt. Now on the right, this is 1/10 times x, right? So I haven't taken the derivative yet on the right. So that negative sine of theta, d theta dt, is equal to 1/10 dx dt. Oops. And the thing is I want to solve this thing for d theta dt. I want to get that by itself. Well, you know, all I have to do is divide both sides by the negative sine of theta, right? And by the way, because I'm dividing by the sine of theta, I can say the sine of theta, in this case here, is 6 over 10, which is what? 3/5. Okay, that's the ratio. So I can say d theta dt is equal to dx over the negative sine of theta times dt times 10. So negative 10. Forgot the 10. Right? These two are on the denominator. If I'm multiplying both sides by, or sorry, dividing both sides by negative sine of theta, then sine of theta is going downstairs too, right? So d theta dt is equal to 1 over negative 10 times 3/5 dx dt. With me on that? So I did this for a reason. Normally I wouldn't write this out like this. I would just do 1 over negative 10 sine theta dx dt and leave it like that. But I just wanted to show you, to keep things straight, that, you know, these are in the numerator, those are in the denominator. Anyway, maybe I went overboard. So d theta dt is equal to, I'm going to put the negative up here. So I've got 1 over 35ths. Now look, 5 goes into itself once, it goes into 10 twice, and 2 times 3 is 6, right? And dx dt was given as 2. So we get negative 2 over 6, which is negative 1/3. So what I can say, so to go back to the question was, at what rate is the angle between the ladder and the ground changing when the base is 8 feet from the house? Well, it's changing at a rate. So theta is decreasing, right, at a rate of 1/3 radians per second at the moment when the base is 8 feet from the ground. Let me just check my work. Boy, this thing goes on and on and on. Yeah, they have the same thing. All right, they have the sine of theta is 3/5, which we have here. So the answer is negative 1/3. All right. So that's a theta problem. Let me see if I can find, I have my file up here. My related rates, practice. Oh, no, not that one. Not that one. So sorry about this, you guys. Oh, here's a theta problem. Okay, so let me print this. Print. Okay, so bear with me in my printer for a second. I just found a really old practice set, like from 1988. This is actually, I guess, from the 1988 AP Calculus exam. I'm assuming, because I don't remember. Let's look at this. All right, so I'm going to cover this up because the solution's there too. All right, so back to this thing. Okay, so it says the figure shown represents an observer at point A watching a balloon as it rises from point C. Okay, so this is kind of like the rocket problem, right? The rocket went up, the balloon's going up, okay? Now, this is already pre-labeled, so ignore that for a second. The balloon is rising at a rate of 3 meters per second, and the observer is 100 meters away from point C. So, again, here's the observer. He's 100 meters away from this point here, C. And I guess this is point A, since that's what they said. And this is my B for balloon. And the balloon is rising, right? And what I know is that dy dt, because that's the y direction, is equal to 3 meters per second, right? The observer's 100 feet away. So first of all, they want you to find the rate of change in x at the instant when y is 50. So they want to find dx dt when y is 50. Well, if y is 50, and I'm just going to go ahead and find z2, right? This is 100 squared plus 50 squared, so 2,500. Yeah. Z is the square root of 12,500. So I just leave it like that if it doesn't come out perfectly. All right, so everything is labeled. So again, they're calling this X. You can use this or not. Find the rate of change in X. Oh, I see. All right. So I'm going to change this to Z when Y is 50. All right. So I'm looking for dz dt. Sorry, I guess I should have gone with their picture. But I always call hypotenuse Z. Okay, well, this is a triangle and it's a right triangle. And I know that x squared plus y squared is equal to z squared is going to be the ticket. And I also know that this is my x, this is my y, this is my z. This is constant, right? So I have 100 squared plus y squared is equal to z squared. And if I take the derivative, this becomes a 0. So I get y prime is equal to z prime. I'm trying to solve for z prime. So I've got 50 times 3 is equal to the square root of 12,500 z prime. Oops, sorry. So z prime is going to be equal to 150 divided by 12,500 under the radical. And that's going to be, let's see, 150 divided by, so z prime is 1.342. All right, so the rate of change of that distance between the observer and the balloon at the instant when the balloon is 50 feet high, let's say, is 1.342 feet per second. They're not even given units, so you don't need to worry about units. Then they want you to find the rate of change of the area in the triangle at the instant when y is 50. Ooh, now we've got to use a different formula. The area of a triangle is 1/2 base times height, right? And so what I'm going to have to do here, the base of this triangle is constant. So what I have is A is equal to 1/2 times 100. Now the height changes, right? As the balloon rises, the height's going to change. So anyway, at this point here, I can write this as A is equal to 50h. And now I can take the derivative, dA dt is equal to 50 dH dt. Let me make sure I read that right. Find the rate of change in the area of the right triangle at the instant when y is 50. Yeah. So my y, so I'm calling it dH dt, this is going to be 3. So the change in area with respect to time is 50 times 3, or 150 square meters. Because remember, this is getting bigger, that's getting bigger, so the area of the triangle is going to increase as well. Now, what I wanted to get to was find the rate of change of theta at the instant when y is 50. Okay, so there's a theta here. And again, as the balloon rises, that angle between the observer and the balloon is going to increase, right? So once again, I have this little triangle, and I can call this theta, right? And this is 100, and this is 50, and this is the square root of hell. And so I can use a sine, a cosine, or a tangent if I want to, all right? And remember that when I choose my trig function, I want to include the constant. And so a cosine would be nice, right? And the sine wouldn't include the constant. That's the issue. So I want to include that constant, and I want to include a variable. This is my x, this is my y, this is my z, right? So what I can say is that the cosine of this angle is equal to the side adjacent over the hypotenuse, right? So this is 100, oops, over z. This thing changes, that thing's constant. All right, so this is the function I'm going to use. Now, the other thing I could use is I could say the tangent of theta. So let me just show you a tangent, okay, is y over x, right? But x is constant, so the tangent of theta is y over 100. Tangents are, sorry about it, tangent's a really good one to use. Let's use the tangent so you can see a tangent in action. Okay, so I have a function, right? So let's take the derivative of the left and right. So the derivative on the left is going to be secant squared theta d theta dt is equal to 1 over 100 dy dt. All right? So d theta dt is equal to 1 over 100 secant squared theta dy dt. Now I know the rate at which y is changing. It's 3 meters per second, right? So I can plug in a 3 there. What I don't know is the secant thing, right? I don't like secants. We feel very uncomfortable with secants. It's no problem because the secant is 1 over the cosine, all right? So what you could have done was you could have said this is 1 over the cosine squared of theta and then multiplied both sides by that reciprocal. So really what you have then is d theta dt is equal to the cosine squared of theta, right? This is 1 over the cosine, so you flip it and it goes on top, over 100 times 3. You with me on that? All right, well, what's the cosine of this angle? Well, the cosine of this angle is 100 over root 12500. The thing is we've got to square it. So if we square it, the top is 100 squared and the bottom gets rid of the radical. So what we have here is d theta dt is equal to 100 squared over 12,500. Sorry, I know my hand's in the way. I've got a book in the way here. Let me move this over. So I'm going to work over on this side. Sorry, d theta dt is equal to, so the cosine squared is 100 squared over 12500 over 100 times 3, which is my dy dt. So what this is going to be is this 100 is going to cancel with one of those 100. So we've got 100 over 12,500 times 3, which is 300 over 12,500. I can cancel a 0 for a 0, so I get 3 over 125. And what is that? 3 over 125. Okay, so I can say the rate at which the angle is changing at the moment when y is equal to 50 is 3 1/25. All right, I can say it's increasing. So let me show you this. Do they oh, they don't have the solution? That's not the solution? Yeah, here it is. Okay, so generally, so we're right here. Generally, the tangent is a really nice function to use. All right, we take the derivative of the left, we get secant squared. And the nice thing is that, remember that secant squared can be written as 1 over the cosine squared or you know, if you rewrite that as 1 over the cosine squared of theta dt, then what you're actually doing is multiplying both sides by the cosine squared, so it goes up top. And you know how to find a cosine of a triangle. All right, so I'm going to stop there because it's 10 o'clock. I've been working since about 5:45 this morning, so I'm just on the border of delirious. Try the problems in WebAssign. They're due on Friday. If you need help, I will help you. And also go into the AP classroom. And I found, after many hours, an FRQ on the topic of related rates, right? So go in there and ponder that and try and work that one out. Now, that's a participation grade at this point. Soon I'm actually going to grade those because your test is going to mimic those. So those are really important. But I understand that this topic is a little bit for some of you still. So I just wanted to make sure you feel more comfortable with the material. So I'm going to grade the AP classroom on participation. WebAssign, they're easy enough that you should be able to get a good grade. So those are going to be graded for grade. The AP classroom this time will be participation, the next set. I'm going to do a timed mock exam with you guys because remember you have 25 minutes, right? 25 minutes to solve the problem and 5 minutes to upload it. And if it's a second late, no matter what the reason, it's too bad for you. You don't get any points. So I want to get you used to that timed situation. And so probably at some point next week, we'll have fun and do a timed one to see how you feel about it. Anyway, I'm going night-night. So you guys have a great night, and I'll see you mañana.